Let's go on. Last time we talked about complex manifolds, and we have seen that there is the complex structure operator on every complex manifold. And then we have, so I have stated the theorem of Newland and Nirenberg, and so today I want to talk a bit more about this, and in particular I want to show you a proof of this theorem in one particular case, which is most important for us, namely in the real analytic case. And the proof is relatively easy in this case, so I will probably be able to explain it somehow relatively completely. Probably it will rely on some analytic results, but nevertheless the idea I think will be clear. But first of all, so before I do this proof, I want to talk a bit more about this complex structure operator. Again, so let's consider C infinity manifold. So a C infinity manifold M of real dimension 2m, and assume that there is an endomorphism of the tangent bundle, which we denoted by I, capital I last time. So I just recall this definition once again. So this I, which is a global section of the bundle of endomorphisms of Tm. So Tm is the real tangent bundle of M. So this is called an almost complex structure. If I square is equal to minus identity. Such complex structure exists on any complex manifold, as we have seen last time. So and now we also have seen this decomposition of the complexified tangent bundle. So let me write it down again. So first I will introduce some notation. So notation will be like this. So the complexified tangent bundle will be denoted like this. So this is just Tm tensor C. So I just tensor this bundle with C fiber-wise. So I just complexify all the fibers of this vector bundle. And the dual, the cotangent bundle, I will write sometimes T star M or lambda 1 M. So this is the cotangent bundle. And its exterior powers will be denoted by lambda Pm. So I think that this is quite standard. And well, the complexification will be again denoted like this. And we have for any local section of TCM, we can consider its 1, 0 and 0, 1 part. So I will just emphasize again. So sometimes this notation code is confusing. So such when I write something like this, this means that I just take a local section of the bundle or of some sheaf. So this means that V is...
А можно вас сфотографировать быстренько? Я пойду.
Давайте. Хорошо.
Да, может пройти. Видите, что я переживаю? Можете чуть сюда посмотреть. И фото ставить туда. Ага. Да?
Пожалуйста. Okay, sorry. I wanted to say that, so when I write something like this, I just mean that V is a section of this bundle. Over some open subset. In M. Okay, so I'll just write it shortly like this. And then, so if I take this V, then I can consider its 0, 1 and 1, 0 parts that are defined as follows. So 1, 0 part is 1/2 of V minus imaginary unit times IV, and 0, 1 part is 1/2 of V plus imaginary unit times IV. So these two operators that map V into V10 or V to V01, they are projectors onto the eigenspaces for this complex structure operator I. So this gives me a decomposition of the complexified tangent bundle into the direct sum of T10M and T01M. Right, so this map just I map V into V10 plus V01. And of course, the complex structure also acts on all other bundles that are obtained from Tm by tensor operations, for example, on lambda 1. So the action on lambda 1m is given like this. So if I have a section of lambda 1m and a vector field, well, in Tm, and then I apply I to alpha, and I again get a 1 form whose value on this vector v is just alpha of I v. So as usual, you usually define the adjoint operator. So this I somehow acting on alpha is the adjoint of I. And then I also can decompose lambda 1m into 1, 0 and 0, 1 part. So lambda 1m complexified. And sorry? Can you please rotate? Okay, so yeah, all right. So then I will denote by lambda p Q the following thing. So I take the exterior powers of lambda 1, 0 and lambda 0, 1, and I will write lambda PQ M for the tensor product of the pth exterior power of lambda 1, 0 M and qth exterior power of lambda 0, 1 M. And using this notation and using this decomposition of lambda 1, I get the following thing. So if you think about how vector space is somehow, if your vector space is a direct sum of two subspaces, and you take an exterior power of this vector space and it decomposes like this. So if I take lambda k cm, then this will be isomorphic to the direct sum of lambda pq m. The sum is over OP plus Q equal to K. And then also, well, let's also remark that I restricted to this bundle lambda PQ is just multiplication by imaginary unit to the power P minus Q. So this follows simply from the definition, because when you take, I acts on this thing as the imaginary unit, and on this thing as minus the imaginary unit. When you take exterior powers, so this action is, so you take the power of the imaginary unit, and so this is the right power here. Then we will also use de Rham differential. So we have de Rham differential. And we can also decompose it into, so we can write a PQ decomposition for the de Rham differential. So of course, if you apply D to some to some K form of type PQ, then you get a priori a sum of somehow forms of types, you know, PQ, where P plus Q is K plus 1, but in fact somehow there is the following lemma that for any form of type PQ, d alpha will be somehow, it will decompose into a sum of forms of different PQ types, but there will be only 4 summands in this sum. So a priori there could be more. So this will be lambda P minus 1 Q plus 2 plus lambda P Q plus 1 plus lambda P plus 1 Q and lambda P plus 2 Q minus 1. So let's prove this. Yeah, I also wanted to remark before. So when I write this PQ decomposition, I always also somehow it's just a matter of notation. So lambda PQ is 0 if P is less than 0 or Q is less than 0, or if P plus Q is greater than the dimension of the manifold. So somehow this lambda PQ is defined like this only when it makes sense. And otherwise, if it happens that, for example, I take P equal to 0 here, then I get something of type -1 Q plus 2, and this is 0, so I'll just always mean that this is 0. So P less than 0, Q less than 0, or P plus Q is greater than the dimension of M. So using this convention, I can just always write it like this. So why is this true? Well, first, that is obvious for the case when PQ is 0, 0, or 1, 0, or 0, 1. So why? For example, if I take 0, 0, then this is a 0 form, namely a function. And then if I take the exterior differential of a function, I get a 1 form. And for 1 forms, I have this decomposition, right? So it is always just lambda 1, 0 plus lambda 0, 1. And I have these two summons here, written here. So this is lambda 0, 1, and this is lambda 1, 0 for the case when PQ is equal to 0, 0, right? And similarly, so I write so clear because lambda 1 is just this direct sum. And also it is clear because if I take somehow the lambda 2, then what will this be? This will be lambda 2, 0 plus lambda 1, 1 plus lambda 0, 2. So again, if I have either this or this, then in this claim I just have all the summons. So for example, if I take 1, 0, then I get here 0, 2. Here I get 1, 1, and here 2, 0, and this will be just 0, and so on. So that is clear. And in general, it follows just by Leibniz rule, because the de Rham differential satisfies Leibniz rule. So locally, I can write alpha is a sum of forms of the following. Somehow it takes the form alpha 1, which alpha 2, and so on, which alpha P, which beta 1, and so on, and beta Q. And these forms are, so these alphas are, alpha I are of type 1, 0, and beta J are of type 0, 1. And then I take the differential of this thing, and then I get a sum of the following form. So this is my form written there. And I get a sum. Here I get some signs. and then I should substitute the differential of alpha k somewhere in the middle, and then also the same with these betas, so there will be again some sign. And I'll have a differential of beta k somewhere in the middle. Okay? So then you can check that actually all the summands, they satisfy this condition. So all summands satisfy the claim. Well, for example, if I look at the summand of the form alpha 1 and so on, and here I have d alpha k up to alpha p and then beta 1 and so on up to beta q. So what is the type of this form? So this is so alphas are of type 1, 0. So I have so this is of type. So I have alpha 1 up to alpha p, they are of type 1, 0, and then there is this differential of a 1, 0 form. So I will have, there are p minus 1 alphas without the differential, and then plus. So this d alpha k, so we know that it is a 2 form, so it will decompose into types like this. So then I get plus 2 and then comma q, so I always have q plus there will be type 1, 1. So this is p minus 1 plus 1 comma q plus 1 and plus p minus 1 and q plus 2, right? So this is just p plus 1 q plus p q plus 1 plus p minus 1 q plus 2. And that is somehow, that is part of this direct sum written here, right? So I have p plus 1 q, p q plus 1, p minus 1 q plus 2 here. So this summand here satisfies this condition, and analogously for the other summand. Okay, so right. Now, if we write this decomposition for the differential, so I will not write this computation for the other summand, so you can do it yourself as an exercise. So then, as a corollary, we get a decomposition of the Durham differential into 4 types, minus 1, 2, plus 0, 1, plus 1, 0, and plus 2, minus 1. Right? Every of these components is just the composition of the exterior differential from PQM into lambda P plus Q plus 1M, and the projection onto the corresponding, somehow onto the component of the corresponding type. So this is RS, so I should go into P plus R, Q plus S, M. Yeah. And then I claim, so this is another lemma, that for any form of type PQ and any function d minus 1, 2 of f alpha is f times d minus 1, 2 alpha, and d2 minus 1 of f alpha is f times d2 minus 1 alpha. So these these two components of type minus 1, 2 and 2 minus 1, they are linear over the sheaf of functions. In particular, they define a morphism of vector bundles. So so they give morphisms of vector bundles from lambda P Q M into lambda P minus 1 Q plus 2 M, and the other one is from lambda PQ into lambda P plus 2Q minus 1. So the RAM differential is not a morphism of vector bundles, I recall, because somehow it's not linear over the structure sheaf. It instead of this somehow linearity condition for the full de Rham differential, you would have an exterior derivative of f appearing here in a similar formula. But for these two components, so these two components are linear. So let's check this. So, okay, so for example, so let's do it for the minus 1, 2 part. This is by definition, so what is it? I apply the usual differential and then I take the p minus 1 q plus 2 part of it. So then I have here df wedge alpha plus f d alpha so here this form, so what is the type of this form? It is, so this is 1, 0 plus 0, 1, so I get p plus 1 q plus p q plus 1, so I have components only of these two types here, and when I take here the component of the type p minus 1 q plus 2, I get 0. So the only thing that remains is this second summand, and of course taking taking the projection to the one of the PQ parts, so somehow the projection operator is linear over the structure sheaf, so it's a morphism of bundles. So here I can just write it like f times d alpha and p minus 1 q plus 2 part, and this is by definition d minus 1 to alpha, right? And analogously for the other, analogously for d2 minus 1, exactly the same computation proves that it is also linear. Okay, so now we come to this integrability condition for the complex structure. So this decomposition, so this is true for any almost complex structure. And now I mentioned last time already the condition of integrability, which is satisfied on any complex manifold. So let's now reformulate this condition in terms of this differential. But before I do this, I just want to recall, well, just in case someone has forgotten, so we will work a lot with Lie derivatives along vector fields. So let me just recall some properties of the Lie derivative. So if I have a vector field, let's say U, so a section, a real vector field, a section of a real tangent bundle, so then I can integrate it, at least locally, to a flow of diffeomorphisms. So it can be locally integrated to a flow of diffeomorphisms so any point, for any point in M, there is a open neighborhood let's call it, for example, M0 in M. It's a neighborhood of X, and a smooth family of diffeomorphisms depending on T. So where T is a real number, so a small real number, somehow epsilon is some constant, so for some epsilon greater than 0. Well, the diffeomorphisms integrate the vector field in the sense that for any, now, for example, point y in this neighborhood, if I look at the trajectory of y, then this is the integral curve of this vector field. So this thing t goes to phi t of y is the integral curve of u passing through y. Right, so then I integrate my vector field and I get some curve which is tangent to this vector field and so this is the point y, right, like this. And then I can pull back tensor fields along this flow of diffeomorphisms. So for any tensor field, some tensor power of Tm and some tensor power of the cotangent bundle, I can pull back this T along my flow. So this is tau, and this is phi t upper star, and then I can compute the derivative of this at the point t equal to 0, right? So I'll get again a tensor field of the same type, and this is called the Lie derivative, which I will denote like this, Lu of tau, right? So this is the Lie derivative of tau. We'll just need some properties which I will recall quickly, because we will use them all the time. So if I have, well, first of all, how does this Lie derivative act on functions and on vector fields? So if f is a function, then the Lie derivative of f, well, you can write it like this. You take df, you take the exterior derivative of f, and then you take the convolution with the vector field u, so that is df of u. And if you have a vector field, let's say v, then Lu of v is just the Lie bracket of u and v. Also, of course, there are some usual properties. So this Lu is linear in u, so I'll just write it like this. Also, it satisfies Leibniz rule. So if I have some tensor fields, tau 1 and tau 2, for example, if I take the tensor product, and this will be Lu tau 1 tensor tau 2 plus tau 1 tensor Lu tau 2. It also, of course, commutes with convolution of forms and tangent vectors, and in particular, if I apply, so for one form alpha and the tangent vector v, I get that Lu of the convolution of alpha and v is Lu alpha of v plus alpha of the Lie bracket. Okay. And then the most important thing is Cartan's formula. I recall it here. So this will be 4. So if I take the K form on M, then Lu of alpha can be written as differential of u convolution with alpha plus u convolution with d alpha. So this convolution map just means, so it maps a k form into a k-1 form, and it works like this. So okay, so I'll just write it as follows. For some other vector fields, for example v1 and so on, vk-1, if I take the convolution of alpha and u and apply it to these vector fields, then this is simply alpha applied to u, v1 and so on, vk. vk-1 here, right? Like this. So,
may I ask
yeah?
a question? So, maybe very strange. So, phi upper star is a pullback of the form.
Yes, I think that you should take the pullback.
And what does it mean to take a pullback of a vector field?
This means that you take phi inverse because it's a diffeomorphism and apply the push forward. So if you have a diffeomorphism, yeah, right. So usually you somehow pull back differential forms and you can push forward the vectors, right? But if you have a diffeomorphism, then you can also pull back vectors because you can take the inverse. Okay, more questions? So now, well, let me recall the definition first. So from last time, that an almost complex structure I is integrable if the subbundle of 1-0 forms is closed under Lie bracket. So for a pair of vector fields of type 1-0, the Lie bracket is also of type 1-0. And we have seen last time that this is obviously satisfied on any complex manifold. So if you have somehow if you cover this M with charts and the transition functions are complex analytic, and if you have a pair of 1-0 vector fields, which means that they are just the usual holomorphic vector fields, of course a bracket of two holomorphic vector fields will again be a holomorphic vector field. Right, so now on an arbitrary almost complex manifold this is not true in general, and the condition, so this integrability condition can be rephrased in terms of de Rham differential like this. So proposition, so the following conditions are equivalent. First is that I is integrable. The second condition is that for any alpha, I want to take a form of type 0,1. The differential. So as we have seen before, it will be of type 0,2, 1,1, and 2,0, right? In general, but then I want to ask that this is only of type 1, 1 plus 0, 2. And the component of type 2, 0, the component of type 2, 0 vanishes. Or I can also rewrite this as follows, that these two components of the Dirac differential are trivial, right? So let's prove this. Of course, these two conditions, 2 and 3, they are equivalent quite obviously. So 3 implies 2 is clear just because somehow 2 is exactly the condition 3 for the forms of type 0, 1, right? And 2 implies 3 again, just as we did, in the previous proof by using Leibniz rule. So this is clear. And 2 implies 3 by Leibniz rule. Well, Leibniz rule and possibly also taking complex conjugation. Of course, if you have this condition 2 for the forms of type 0, 1, well, you can write down a similar condition for the forms of type 1, 0 just by conjugating. So Leibniz rule and complex conjugation. So just do it as an exercise. That is quite easy. So essentially we just want to prove that 1 is equivalent to 2. So first, okay, so let's show that 1 implies 2. So assume 1. I is integrable, so we have this condition written here. And now we want to prove that d alpha, so alpha is like in this second part, so of type 0, 1, and we want to show that d alpha to 0 part vanishes, right? So how to prove that somehow some part of the differential form of type 2, 0 vanishes? So we can apply this d alpha to a pair of vector fields, and this vanishes if and only if for any pair of vector fields we get 0, right? So this is equivalent to the following condition, that for u and v in t1, 0 of m, d alpha of u v is 0. Because if I take this d alpha and I plug in two vector fields, but these two vector fields, they are of type 1, 0. Somehow if I plug a 1, 0 vector field into a form of type 0, 1, then I get 0 automatically. So this, when I apply this pair of vector fields to d alpha, this is the same thing as first taking the 2, 0 component and then applying these vector fields, right? So that is exactly what I want to check. So that's what I want to check. And now let's deduce this from integrability, and that's using Cartan's formula. So let's do the following computation.
Можно вопрос?
Да.
Немножко упустил из внимания.
Да.
Извиняюсь, что на русском.
Да, пожалуйста.
А там скобки должны быть квадратные, где дифференциал, или... Да.
Нет, здесь скобки круглые. Вот я имею в виду, что я просто подставляю дифференциальную форму два векторных поля.
Все, я понял.
То есть d альфа это два формы, а я могу в нее подставить два векторных поля, получить какую-то функцию.
Я понял, да, все хорошо.
Угу. Okay, so let's do the following computation. Let's take the Lie derivative along u of alpha of v, I think. So, well, first of all, alpha is of type 0, 1 and u is of type 1, 0, so that's 0 here. So this is on one hand, this is 0. On the other hand, I have again Leibniz rule, right? So this is Lu alpha of v plus alpha of the Lie bracket. And now I use Cartan's formula written on the left hand side in the first line. So I get d of, well, convolution of u and alpha is just alpha of u, and then I take this d of alpha of u and plug inside of it, plug v inside, right? And then plus u convolution with d alpha, and I also have to plug in v. And so that's the first summand here, and the second summand I copy it. Okay, so again, so here I have alpha of u, and u was of type 1, 0, alpha was of type 0, 1, so this is 0. On the other hand, here, by the definition of convolution, which is also written on the left blackboard, I get just d alpha of u comma v, and here I get alpha of the Lie bracket of u and v. So that's all. Now I assume 1, so I assume that this thing is also 0. The bracket of u, this thing is also of type 1, 0, right? And then this vanishes. So this assuming 1. And in this case I get this equality, right? So we get the alpha of u v is 0. And conversely, also the same computation works, right? So if we now assume that this part of the differential vanishes, then we can again do the same computation, and we can conclude that this summand is 0. So then I get that this alpha of the Lie bracket is 0 for any pair of 1, 0 vector fields and for any alpha. So for any form of type 0, 1. And this exactly means that this Lie bracket of two vector fields is of type 1, 0 again. So 2 implies, so this we get this, so this is 2, right? And 2 implies 1 by the same computation. Okay? Or should I explain it once again?
Just a couple of seconds.
Mm-hmm.
Yeah, that's good.
Okay, so any questions from Zoom maybe? So, okay, so then well, think a bit about this if you haven't seen this computation before. And also I should remark maybe that, so here, this component of the RAM differential, or well, one of the two components, usually in the literature you can somehow you can find a condition, the same condition written in a different way a little bit. So I'll just write it as a remark. So the dual of d2 minus 1, which goes from lambda 0, 1 into lambda 2, 0, right? So the dual of this thing is called a Nienhuis tensor in the literature. So this is usually denoted n sub I. So this is some tensor field defined for any almost complex structure. So it goes from lambda 2 of t1, 0 into t0, 1. That's exactly the dual. And the condition is that the complex structure is integrable if and only if this tensor field vanishes. So that's exactly what we prove, because an operator somehow vanishes if and only if its adjoint vanishes. So that's the traditional terminology. And now, after this discussion, well, you can probably do some exercises. Well, as an exercise, you can think of, well, think how to construct probably an almost complex structure that is not integrable. An example of an almost complex structure that is not integrable. And then also you may observe, well, it's almost obvious from what was said, but well, think about it. If it is not obvious, that in the case when M is two-dimensional, any almost complex structure is integrable. So if M, if the dimension of M is 2, then any almost complex structure is integrable. Maybe you can also check that this condition, from the condition of integrability, it can be written in the following form. So if and only if the following expression vanishes. So now I take, well, let's say I take two real vector fields. Well, let me call them by some other letters, x and y, for example. So these are real vector fields. And the expression is the following one. So the bracket of xy plus I times the bracket of somehow I, x, and y and plus I, the bracket of x and iy, minus ix, iy is 0. I'm not sure that I have copied this correctly. Okay, well, never mind. So then let's just remove this thing. So I don't want to confuse you because I'm not sure of this expression. So let's just leave it like this. Well, essentially the idea is that you can rewrite this condition in terms of real vector fields and this complex structure I. Okay, so now let's go on and prove. Yeah, so probably are there any questions again? No. So let's prove this theorem of Newlander-Nirenberg. I want to show you some, probably at least a sketch of a proof in one important case. So let me first recall the statement, although I mentioned it last time. So let me write it here, a theorem. Newlander-Nirenberg. So if I is an integrable almost complex structure on M, then M admits a structure of a complex manifold such that I is the corresponding complex structure operator. So if we have a complex manifold, somehow the meaning of this is that, again, somehow we can cover M with some charts with values in C, M in such a way that the transition functions are holomorphic. So somehow we start from a real manifold and this section of the endomorphism bundle of the tangent bundle that just satisfies essentially a linear condition that somehow some tensor field somehow some tensor field constructed from this almost complex structure vanishes. And then the conclusion is that I can find this system of holomorphic charts, and then I have a well-defined notion of a holomorphic function on this manifold and so on. So that's a non-trivial result actually. And it's difficult to prove. So in general, recall that we have started from arbitrary M that was just a C infinity manifold. So it's quite complicated to prove this in general. And now I will just make an additional assumption before proving this. So we prove the theorem assuming that M is a real analytic manifold. And I is also real analytic. So what does this mean? So a real analytic manifold. So recall this definition of a manifold. So we covered our topological space with charts, and we asked for the transition functions to be smooth. So I can as well ask these transition functions to be real analytic. So, so this means that M has an atlas well, just as last time, it consists of some open subsets in M, and these phi I are homeomorphisms onto some open subsets in R2M. But now I ask that the transition functions, such that the transition functions from phi beta of U alpha beta into phi alpha of U alpha beta, so these are real analytic. So this just means that these maps are given by power series in the neighborhood of every point. So if I have a map F from some open subset in Rn into Rn, well, this F is real analytic if for any point in U somehow F, so there exists some smaller subset U prime containing this point such that for any Y in U prime, F of Y is given by some convergent power series. F, well, let's say somehow with index J or multi-index J times Y minus X to the power J. So J is some multi-index, well, J is an n tuple J1 and so on Jn, and then this notation means that so Y minus X to the power J is just the product of the coordinates yi minus xi to the power ji, right? So that's, well, for example, you can think about the one-dimensional case, and this just means that somehow f is given by convergent power series, and this fj are real numbers. So the power series is well, converging. Converging, or absolutely converging in U prime. And then in this case, yeah, I can somehow, if I have this, then I can ask for the tensor fields, the functions, the vector bundles also to have real analytic structure, meaning that all the somehow locally any tensor field can be given by a map from U alpha to some vector space. And I can always ask that this map is real analytic in the same sense that in a neighborhood of every point it can be decomposed into an absolutely convergent power series. Okay, so in particular this I is real analytic. If I locally is given by a matrix consisting of real analytic functions. Okay, so that's my assumption now. I assume that everything can be decomposed into power series. Okay, also I will now use the following notation. So let me write it here. So now I will always now assume that I is integrable, so all these conditions of the previous proposition are satisfied. So I have only two components of the Dirac differential, namely the component of type 1, 0 and the component of type 0, 1. And I will denote these two components as follows. So notation, so D1, 0 will be denoted by the following curly D or del, somehow this letter, and D01 will be del bar. So then D is del plus del bar in the case when I is integrable Okay, so now let's do the proof, assuming everything is real analytic. Sorry, a question? Ah, okay. Okay, so it's a bit long. Let's do it in several steps. So step one. So how to prove that I have a structure of a complex manifold? We have discussed it a little bit last time. So we can either construct these charts or we can describe the structure sheaf. So you remember maybe, so we have introduced the structure sheaf on any complex manifold and said that somehow locally the local sections of the structure sheaf are functions that are holomorphic in every chart. And one way to introduce a structure of a complex manifold is just to define a subsheaf in the continuous functions and then prove that this sheaf is locally isomorphic to the sheaf of holomorphic functions on an open subset of Cm. So, that's the way we want to do it. So we denote by, so we denote by C omega m the sheaf of real analytic functions. On M. And now inside of this sheaf of real analytic functions we want to produce a subsheaf of holomorphic functions. So we define the structure sheaf of M as a complex manifold as follows. We take those functions over some open subset U such that, so the condition is the usual one, of course, as in complex analysis, that this del bar F vanishes. But now our del bar is the operator defined in terms of this almost complex structure. So for U open in M. So we have not identified this U with a subset in Cn. So this is not the usual condition that the function is holomorphic so far. We now need to prove that this OM is locally isomorphic to the sheaf of holomorphic functions in Cm. Right? So, well, I mean, this sheaf could be, for example, trivial. I don't even know so far that there is at least one non-zero or non-constant, let's say, function, which is a section of this sheaf over some open subset U. And that's what we want to prove. So now let's just, I mean, somehow we're using these real analytic charts. We can embed U into R2M, right? So this we have. We may assume that U is now an open subset of R2M. So we have everything defined on this open subset. So we have coordinates x1 and so on x2m. And let's denote by V1 and so on Vm. The vector fields that span this subbundle T10M. Well, some local basis of T10M. Okay, so we may also assume that somehow we are working in a small neighborhood of some point. Let's say this is the point 0 in R2M. This U is just a neighborhood of the origin. And we want to show that this OM is locally isomorphic to the sheaf of holomorphic functions after identifying R2M and Cm in some way, somehow. We may always shrink this U if necessary and pass to a smaller neighborhood, because after all we will cover M with such neighborhoods. So it doesn't matter how small they are. So now the first step is to define the sheaf, and now well, let's check the condition. So step 2 is the following thing. We claim that there exist M functions. Well, I didn't say this, I guess. Well, the functions, by function, I always mean a complex valued function. So in particular, this sheaf of real analytic functions here consists of functions taking values in C, and F is real analytic. So I want m sections of my structure sheaf such that the differential of the differentials of these functions at the point 0 are linearly independent. Well, so these differentials at one point are linearly independent. As C linear maps. C linear maps. First remark is maybe it's not obvious. So let's remark first. Why are they C linear maps? So this just follows from the condition that the del bar of f vanishes. So let's observe this. So note the following. If f is 0, then df is a map from the tangent bundle of M with this complex structure I into C is C linear. So what does it mean? Somehow this is a complex vector space, because this I gives me the structure of a complex vector space, and C is of course naturally a C vector space. So why is this? Well, it's just because df is d10f. Right, because the 0,1 part vanishes, so this del bar is just by my notation is d01. So then I can apply this to some vector field I can, okay, let me write it like this. I can just take some vector in Tm and write down the conditions that del bar f vanishes. So I take df of v plus square root of minus 1 iv. So this lies in T 0, 1. And so this must vanish because df is of type 1, 0, right? And so this means that this is df of v plus square root of minus 1 df of iv. And this implies that df of iv, so it will be minus somehow minus, well, I have to multiply by the imaginary unit first, and then I get imaginary unit times df of v. But that is exactly the claim that the differential is C linear, so somehow the complex structure acts by the operator I on the left hand side, and on the right hand side it acts just as multiplication by the imaginary unit, right? So that's the C linearity condition. And so that's just the explanation of what I mean here. So I mean that these differentials now, they should be linearly independent, just as linear maps of complex vector spaces. And I have m such maps, and this complex vector space has dimension m, right? So the real dimension is 2m, the complex dimension is m. So the differentials, somehow they form the basis of the dual space. Okay, so how do we do this? So the proof of claim proof of the claim. So how do we find this vector, these functions? So let's write these vector fields. So look, these vector fields span T1, 0. So let's take their complex conjugates. They span T0, 1, M. And let's write them in the following form. So they are just given by some convergent power series. By assumption, everything is real analytic. So I can write. So my notation will be like this. And these Aij's are some real analytic functions. So d over dxj's, they form a basis in the real vector fields, and these Aij's are real analytic complex valued functions. So these Aij's are given by power series. So in particular, I can now embed my, so this power series, they have some non-zero radius of convergence. And in particular, they define some holomorphic functions, but in a bigger domain. So I can embed my R2M into C2M now, just as a set of real of points with, whose imaginary part is 0. So I take U inside R2M, and I embed this R2M into C2M. And I take some neighborhood of this U inside of C2M. So let's call this neighborhood U plus, for example. So this is open, and this is also open. Well, the picture is like this. I have this R2M, so I have some open subset in it, like this. And then somehow this R2M is contained in C2M, so I complexify everything and take some small neighborhood of this subset. So this here is U, and this is U plus. So U plus is a neighborhood of U inside of U in C2M, right? And then I may assume that these Aij's are holomorphic functions on U plus. Just because in the neighborhood of every point there is somehow this Aij is given by a convergent power series, and the radius of convergence is non-zero, so actually the power series converges in some neighborhood of this point in C2M. So by shrinking u and u plus if necessary, I can just assume that somehow this gives me a holomorphic function on u plus. And so now I can extend all my objects into C2M just because they're given by power series. So this operator I, for example, extends as well. And these vector fields, they will now be holomorphic vector fields on u plus. So Vi bar are holomorphic vector fields on u plus. And also I know that by this assumption that the complex structure is integrable, I have, so by the condition of integrability, I know that the Lie bracket of a pair of vector fields somehow is also a section of T01, but this Vj is a former basis of T01, so it's a linear combination with some coefficients Bijk of Vk bar, somehow like this. And this condition will also be satisfied in u plus, because all the coefficients are somehow, they are again power series, and somehow if the difference between the left hand side and the right hand side is 0, and somehow it is a power series such that it is identically 0 on all real points in C2M, then this power series is just identically 0. So this will still be satisfied in u plus. So this is satisfied in u plus. So again, I have the same condition that these vector fields, they span a sub-bundle inside the holomorphic tangent bundle that is closed under the Lie bracket. Okay? So are there questions about this? So somehow that's the key point, that you can somehow pass to the, now somehow we started from a real manifold, so this R2M, an open subset of R2M, and the idea is to pass to the complex domain. So now we have a complex somehow manifold U plus inside C2M. That's not quite what we want, but using this we may now construct, we may prove the claim that there exist such local functions that satisfy this condition that, well, where is it, that del bar of Fi is 0. Here one uses Frobenius theorem. So there is a well-known theorem in analysis that claims that if you have somehow a system of vector fields which define a sub-bundle closed under Lie bracket, then you can, this is, they define an integrable distribution, and you can always find a change of coordinates such that these vector fields, they are just the coordinate, they become the coordinate vector fields. And this Frobenius theorem, it can be proven in the C infinity setting or in the holomorphic setting. It doesn't matter, the proof is the same. So I want to prove this, of course. So we'll just apply Frobenius theorem to the vector fields Vi bar over U plus. And the theorem claims that there exist local coordinates in U plus I'll call them Z1 and so on Z2M, such that Vi bar is simply d over dzi. Okay? So now I was looking for some functions f1 and so on f1 and so on fm in well, such that del bar of fi is 0. So that's what we are looking for. And so what does this condition mean? Del bar of fi is 0. Well, I can rewrite it as follows. Since this vi bar is span t01, so this is if and only if the Lie derivative of fi along vj bar is 0 for all j. Right, that's just the differential of fi into which I plug this vj bar. And vj bar span t01, so this condition exactly means that this 0,1 part of the differential vanishes. But now if I look at the vector fields in these coordinates, then at least in these coordinates it's very easy to find such functions, right? Because here I goes from 1 to m, so I have only m vector fields and I have 2 m coordinates. So the last m coordinates obviously satisfy this condition. So let fi be just z I plus m, right? So one of these coordinate functions, it obviously satisfies the condition. So for example, if I take z2m, then the derivative of these functions along dzi vanishes for I from 1 to m, right? So I goes from 1 to m. And again, so these coordinates are well, let me write it like this. Well, somehow I wanted to write it in a bit a different way, so I want to write it like this. So this new coordinate that I plus m, it's some function of the old coordinates x1 and so on x2m, like this. Yeah, and then so then I define this fi to be this function, which is one of the functions that define the coordinate change. So we define fi like this. All right, so then clearly by just as I have tried to explain, clearly then the condition that the Lie derivative along vj bar is satisfied. Because you can compute the Lie derivative in any coordinates. Somehow it doesn't matter. If this was true in these coordinates z1, zm, then this will be true also in the coordinates x1, x2, m. Okay, so these are my functions, and the claim was that the differentials at 0 are linearly independent. So now why are the differentials linearly independent? Well, again, I just need to look at what happens in the other coordinates. So if I now, well, let me just define now a map. So define a map capital F from U to Cm, and that is the map with components F1 and so on Fm from U to Cm. Okay, so I claim that I claim that df at the point 0, which is from T0m into Cm, that this is, well, invertible. And this will mean exactly that the differential, so the components are linearly independent, because this complex vector space has dimension m, and this one also dimension m. So this is if and only if dfi at 0 are linearly independent for I from 1 to m. That was my claim. So somehow to prove this, well, I wanted to essentially leave it as an exercise. So so you observe the following. If you now look at the corresponding map from the complexification of this vector space, so the induced map from the complexification of this vector space to Cm is surjective because well, this can now be identified with the tangent bundle at 0 of this u plus. So somehow you see, so I had this 0 here, so this is the point 0, so I had the tangent space at this point, and then I embedded this into C2m, so I increased the dimension twice, and that's exactly somehow the process of complexification of this bundle. So now this is isomorphic to the tangent space at this same point to this C2m, right? And in somehow the corresponding differential now, so this f, so this is surjective because f in the local coordinates z1 and so on z2m is given by just by the projection to the last m coordinates, right? So you just take z1, z2m and you project to the last m coordinates. Well, just by somehow by construction, just because that's how I define the components of this map F. And of course, the differential of this map is surjective, obviously, right? And now, so that's somehow that's an exercise. So let's write this as an easy exercise. That if you have some vector space if T is a somehow with a complex structure I, a vector space with a complex structure of real dimension 2m, and I have some linear map from this Ti into Cm is C linear, and the induced map from T tensor C into Cm, well, which simply maps a vector tensor some complex number into A times AV. So, and the induced map is surjective. Then A is invertible. Okay, so that shows that this condition here is satisfied. Okay, so that's the second step. So I have shown that there are m functions, m sections of my structure sheaf, and they give me some map from U into Cm whose differential at 0 is invertible. This means that f, this capital F, is a local diffeomorphism from some neighborhood of 0 into some open subset of Cm. Right? We get F, a local somehow diffeomorphism from a neighborhood of 0 in U onto an open subset in Cm. Okay, so are there any questions about this step? So that's essentially our local chart now. So this local chart around this point 0 is given by this function f. That's essentially that's all. So the last step is a formal thing. So I recall that we actually wanted to prove that this sheaf, which I defined OM, it's a sheaf, well, OM of U, consisting of functions that satisfy this condition. So I need to prove that this sheaf now via f is identified with a sheaf of holomorphic functions on this open subset in Cm. So is identified with the sheaf of holomorphic functions. Well, in Cm. I mean, on an open subset of Cm. So how to check this? I recall from complex analysis, so the condition that a function is holomorphic just simply means that its differential is C-linear, right? Somehow, recall f is a function from Cm, for example, into C is holomorphic if df at every point x in Cm. So this df goes from R to M into R2, right? So I take the differential of this function as a real map. And then, so these vector spaces, they have complex structure naturally, right? Because these are complex manifolds. And so the condition is that this map is C-linear. So that's what we need to check now when we when we identify this sheaf with a subsheaf in the sheaf of functions on Cm. So okay, so how to check this? Let's say we have some function so let's say we have a section of this OM of u. So let's call it G, for example. So let G be a section over U. And so now I want to show that this gives me a holomorphic function on an open subset of Cm. And well, I mean, somehow by identifying this open subset with an open subset in M by F, so I need to prove that the composition of F and G is holomorphic, right? So I first go so F inverse, right? Because I first go from F of U back into U, and then I apply G. So this is my map small f, for example. So why is this holomorphic? So I take the differential of this thing, and then I get the composition of dg and d of f inverse. But though G was the section of this sheaf, so it satisfies this equation, del bar of G equals 0. So as we have already discussed, this condition implies that this differential is C-linear. So this is C-linear. And of course, for f, we have also discussed that this differential of each component of f is C-linear. Then the same is true for the inverse. Well, that's again some simple exercise from linear algebra, perhaps. But, well, that is also C-linear. So then the composition of two C-linear maps is also C-linear. So this implies that f is holomorphic. Okay, so then, okay, I have taken some section of my structure sheaf, and I looked at the function in Cm that this section defined gives me. So I checked that this is holomorphic. So that's one direction, and in the other direction, if I start from somehow now conversely, if I start from some holomorphic function, on f of u on this open subset in Cm. And then I look at G, which is now the composition of f and capital F, right? So I go from U to Cm and then to C. So now I want to check that this G lies in OM, right? But well, then as we have just discussed, the differential of f and the differential of capital F, so this is C-linear. Then this implies that the differential of G is C-linear. And again, okay, so recall our discussion of this condition that the 0, 1 part of the differential of some function vanishes. Well, this is exactly the same thing as to say that d01g or del bar g vanishes. Okay? Well, all right, so that's a quick sketch of the proof of this theorem. So please ask some questions if anything is not clear. So I don't think that we will use the theorem too much. But, well, first of all, well, it is, of course, it is used a lot because you can, well, it's very important practically to have this theorem because you can construct many examples of complex manifolds using it. So, for example, you can construct some complex structures on Lie groups. You can construct some twistor spaces by explicitly describing this operator I, and then you want somehow to conclude that you have a complex manifold. And essentially, in most of the cases, you always have this condition that everything is real analytic. So, essentially, this proof, somehow it works for almost all of the cases which you have somehow practically. But okay, so I don't know if we will discuss any examples of applying this of applications of this theorem.
This is somehow implicit, yeah. So you don't know anything about.
Yes, exactly. So you well implicit, right? But you know this complex structure operator. You don't know somehow. You don't know explicitly the form of the charts in CM, right? So you just claim existence of these charts. But for most of the theory, you don't need the charts. So that's the point, actually. So for our theory, for what we will discuss later. For the theory of Kähler manifolds, you actually don't need somehow to know these transition functions. What you need is exactly this operator I. And somehow you always have it essentially either if you start from a complex manifold, then you have it, or you can just say that you give yourself such an operator I on some real manifold, you check the integrability condition, and then you work with this.
Example in which it's not clear from the beginning that we start from the complex.
Yeah, right. Okay, so yeah, I can think about some example later. So basically,
yeah, because for me it is not. So I mean, probably all of examples that I have in mind are somehow clearly complex manifolds.
Okay, yeah, well, I can give you a hint just right now, so maybe it's not really a precise explanation, but think about the following. So if you have a real Lie group, well, with Lie algebra, G, like this. Well, so you may actually sometimes construct somehow a decomposition of the complexification of G into 1, 0 and 0, 1 part. So assume that you can decompose for some reason the complexification of G into two subspaces, which I call G10 and G01, and such that they are complex conjugate to each other. And assume also that this subspace, for example this one, that this is a Lie subalgebra. So that's exactly the condition that it is a Lie subalgebra, that the Lie bracket lies in G10. So then you identify this G complexified with the space of left invariant complex vector fields on this real Lie algebra Lie group now, right? And then you decompose a tangent bundle like this. Somehow these two things will be left invariant sub-bundles in the complexification of the tangent bundle of G. And this condition means exactly that you have integrability. And so this will give you some left invariant, almost complex structure which is integrable on this Lie group. And this will actually give you a complex structure on G then.
On what?
On G. So you have started from this real Lie group, and for example, you can take some compact Lie group sometimes.
Yeah, well, so let's just take for a second G as SU2.
Yeah, that's right, SU2.
But
which is three-dimensional, so you cannot do this because you will not be able.
So SU2 complexified is SL2 plus. Well, so I kind of have some. Well, but okay, maybe it is not the one wanted, but yeah, but I mean, if you complexify SU2. Then you have such decomposition, but maybe so you claim that it is not a decomposition of okay.
Yeah, right. I'm just saying that yeah, you can start from any real Lie group without any complex structure at all, and in such a way you can construct a complex structure on it sometimes if you can find such a decomposition. So that would be an example where you don't have any complex structure explicitly. Okay, any other questions?
The non-analytic case, how does this theorem?
How to prove it?
Yes, what is the difference?
It's well, it's difficult because okay, so you see, so the key point was that we had those power series, and if a function is given by some power series, then you can complexify somehow. It defines you a function also on a neighborhood of a point in the complex vector space. Just the same power series formally, because if you have a power series like this. Then somehow a priori it was just given for x real, but then you can plug in a complex number into the same power series, and it will also converge in a neighborhood of 0, for example, in this case, right? So that's the key idea, that if all of your objects are given by power series, then you can complexify, and you get you extend the tensor fields to some neighborhood of your point in the complexified vector space.
I mean,
if you don't have this, then you cannot do anything like that. So then you need to use some other ideas.
And are there any interesting ideas?
Well, yeah, there are several proofs. I'm not sure. I'm afraid I can't tell you too much. So, well, essentially, the problem is just to solve this differential equation, right? So you need to find enough solutions to this differential equation. That's the first order partial differential equation. You need to find these m functions whose differentials are linearly independent. And you can solve, well, sometimes you can prove that this is solvable by some analytic methods coming from the theory of partial differential equations. And there is actually a different proof. The idea is to, okay, so, well, the proof would start from an arbitrary I, not real analytic, so C infinity. But then the idea of the proof would be to find some local coordinates in which this I will be real analytic. And you can also prove that you can do that. And then reduce it to the proof that I have shown to you. But that's also a very technical, somehow I don't want to show you these proofs because they are very technical, and somehow there is some hard analysis always hidden in those proofs.
Okay.
Everything is based on the theory of elliptic equations, after all.
Elliptic differential equations.
Yes. Because this del bar operator is elliptic, actually.